ionization energy. Ionization energy. Right, so first we need the definition of ionization energy. The first ionization energy, so this is just a definition. The first ionization energy is the energy required, or needed, is the energy required to remove one electron from each atom in 1 mole of gaseous atoms of an element to form 1 mole of gaseous 1+ ions. Right, so it's quite a big definition. But the important parts are: the first ionization energy is the energy needed or required. That's very important. Energy needed to remove 1 electron from each atom in a mole of gaseous atoms. Okay, so that's the key point, of an element to form a mole of gaseous ions. So let's take an example, right? If we take an example like aluminium, okay, if you are asked to write an equation to represent the first ionization energy, it's going to call it IE, of aluminium, you go, well, aluminium in the gaseous state has to be in the gaseous state for this to be correct. We're going to remove 1 electron. There it is, going to remove 1 electron. And then when you do that, you are left with, when you remove an electron from aluminium, you're left with an aluminium positive ion in the gaseous state. And that's called the first ionization energy of aluminium. And the energy will have a positive number in kilojoules per mole because energy is needed. Positive enthalpy change means energy is needed to remove an electron. Okay, that's the first ionization energy. And then you could do it again, and that's called the second ionization energy. So if you remove a second electron, so you take the positive ion in the gaseous state and do it again, remove a second electron, and now when you remove a second one, you're going to be left with aluminium 2+, like that, and this can happen again. Third ionization energy, take the aluminium 2+, gaseous state, you've got to have the state symbols, otherwise you will not get the mark. Electron plus, now you've removed another electron, and this can carry on until there are no more electrons left. Okay, you just carry on removing them. Okay, now you need to know what the actual value, how this affects the value for the first ionization energy. Right, so I don't know what exactly the value is for aluminium, but let's pretend it's 500 kilojoules per mole, approximately. Right, to remove the first electron from aluminium requires approximately 500 kilojoules per mole. I'm not quite sure exactly what the value is. What will the second ionization energy be? Will it be a number smaller? Will it be less energy to remove the second electron, or will it be more energy? So will it be less energy than the first, or will it be more energy than the first? Which one is it going to be? Okay, so what affects ionization energy, the actual value? So what affects it is the size of the atom. Okay, so if there are more shells, if it's a bigger atom, okay, that's going to have an effect on the ionization energy. All right, another thing that affects the ionization energy is the nuclear charge, which quite simply means the number of protons. Okay, so if there are more protons, there's going to be more attraction with the electrons. Don't get confused. The term nuclear charge, there's also a term called nuclear attraction, which is the attraction between the positive protons and the negative electrons. And that's what keeps the electrons going around the nucleus, the nuclear attraction. So if there are more protons, there's going to be more nuclear attraction as well. And then the last factor as well is electron shielding. These are factors that affect the ionization energy. Electron shielding. Okay, electron shielding is when the inner electrons repel the outer electrons. Okay, because remember, electrons are negatively charged, and so they repel each other. Okay, and this shields, this reduces the attraction. Between the nucleus and outer electrons. So it's like the inner electrons are shielding, protecting the nucleus. Okay, so these are factors that affect ionization energy. Okay, right. So we've just come back to the original question. So if the first ionization energy is approximately 500 kilojoules per mole, when we remove a second electron, is that going to need more energy or less energy to remove a second electron? Okay, so we take aluminium as example, just on your piece of paper, right? So aluminium has got 13 protons and 13 electrons. Okay, so if we remove one of the electrons, we still got 13 protons, but we now have only got 12 electrons. So we've got the same nuclear charge, same number of protons, attracting fewer electrons. Okay, so therefore the nuclear attraction increases, is greater, because it can pull in the electrons, because it's the same number of protons but attracting fewer electrons. The number of shells is the same. The electron shielding is the same or similar. So they don't have an effect, okay? Because if you think, if we do GCSE style electron structure, so GCSE style electron structure for aluminium is 2, 8, 3. So you've got 2 electrons, you've got your nucleus. You've got your 2 electrons in the first shell, then you've got your 8 electrons in the second shell, and then you've got 3 electrons in the third shell. Okay, so the shielding is the repulsion between the inner electrons, repelling and then pushing the outer electrons further away. Okay, so if you take away one of the electrons, the first ionization energy, take away one of the electrons, you still have got 13 protons, but it's now only attracting 12 electrons, and it can pull in further. And so to remove the next electron, so say if we did it again, say if we've got 13 protons and we removed another electron, then that will be even harder, because each time it's getting smaller and smaller. Okay, so the ions are smaller than the atoms. Positive ions are smaller than the atoms. Okay, there's something called successive ionization energy. Successive ionization energy. And this is where you have to be able to sketch a graph showing what is happening when one electron is removed after another after another. So let's do this with aluminium, because this is our example we've been talking about. Okay, so this is ionization energy here, and it's just a sketch, and so we're not putting any values there, it's just a sketch. And this is the ionization number, or the number of electrons removed. You could say either the number of electrons removed. Okay, aluminium has got 13 electrons. You're going to go across 1, 2, 3, 4, 5, 6, 7, 8, 9. Have I got enough room? 10, 11, 12, 13. So we're going to successively remove one electron, one after another. Okay, now, so the first electron that we're going to remove is in the third shell. And that's relatively quite easy to remove. Okay, because it's a long way from the nucleus. So there's not much in the third shell, so there's not much nuclear attraction. It's a long way from the nucleus. The second, we remove that one. The second electron is a little bit harder to remove, a little bit more energy needed, so a slight increase. Okay, so we're still in the third shell, so that's gone. Then we remove the third electron from the outer shell. Again, slightly harder because we've got 13 protons, only attracting now 10 electrons. So there is a steady increase. And these are the electrons in the third shell, in the outer shell. Okay, this bit here, this section here. All right. Now the third shell is gone. We've removed all the electrons in the third shell. It's gone. So now we need to remove electrons in the second shell, and that is a lot closer to the nucleus, and it's a lot tougher, a lot harder to remove electrons from the second shell. So the fourth electron, we need an enormous jump. For the fourth electron, we need a big increase in energy. It's going to be harder, big increase in energy to remove the fourth electron, because it's in a new shell closer to the nucleus. It is in a new shell closer to the nucleus. Closer to the nucleus, right? That's the fourth one. But then we're in the second shell then, so we remove the fourth one, and then the fifth one is a little bit tougher, and then the sixth, and you carry on till all eight in the second shell have been removed. So that's the second shell. These electrons in the second shell, Okay, so now we've removed 10 electrons. Now to remove, the second shell has gone. So to remove the 2 electrons in the first shell is going to be really difficult. So one more. Okay, to remove electrons, so to remove electron 12 is going to be really difficult. I'm going to put it right up there. And 13 is going to be difficult too, and a big jump. So when you have a big jump in ionization energy, that means a new shell. So a big jump, a big increase in ionization energy means that there's a new shell. Okay, so quite often you get questions like, so here's an example, right? So the first, we don't know what the element is, but we know that the first ionization energy is 578 kilojoules per mole, right? All kilojoules per mole, right? The second ionization energy is 1817. The third ionization energy is 2745. The fourth ionization energy is 11,577. 11,577. Okay, and then the fifth ionization energy is 14,842. And then the question says to you, all right, with this information, which group of the periodic table is this element in. So you can see it's increasing about 1,000 or so, about 1,000 difference between first and second, about 1,000 difference between second and third. Then all of a sudden, the big jump between the third and the fourth. So between the third and fourth ionization energy, there is a large increase. It's going up about 1,000, then all of a sudden it's gone up 9,000 kilojoules per mole. There's a large increase. So that means the fourth electron is really difficult to remove. Okay, so the fourth electron is difficult to remove. So that means the fourth electron must be in a shell closer to the nucleus. Okay, the fourth electron must be in a shell close to the nucleus. So that means in a shell closer to the nucleus. So that means that the first three are in the outer shell. So that means it must be a group 3 element. Okay, because the fourth one is really difficult to remove. And the final thing you need to do on this is the trend in the periodic table. Right? So now going down a group, this is kind of quite straightforward. Going down a group, the size of the atom increases as you're going down a group. Okay, so the atomic radius increases as you go down a group, yeah? And that's because you've got more shells as you go down a group. Yeah, there's more shells as you're going down a group. Okay, so therefore you're going to have more electron shielding as you go down a group. Okay, so as you go down the group, the nuclear attraction decreases. Okay, the attraction between the proton and the outer electron decreases as you go down a group because it's getting further away. Now I know you've also got more protons as you're going down the group, but that is outweighed. These two effects, these effects here, are more important, and they outweigh the increased number of protons. Okay, so as you go down the group, it gets easier to remove an electron. Therefore the first ionization energy decreases as you go down a group because it gets easier to remove an electron. Right? Let's go across the period. What's the trend across the period? So across the period, the size of the atom gets smaller. Okay, so across the period, the atomic radius decreases. And it gets smaller because as you go across the period, the nuclear charge increases. That basically means nuclear charge means the number of protons. Okay, the number of protons increases. You're going into the same shell. The electrons are in the same shell. They're in the same shell. The shell's not increasing, and also the shielding is the same as well. They're not increasing as you're going across the period. They're the same. Okay, so therefore, as you go across the period, the nuclear attraction, the attraction between the nucleus and the electron, the outer electron, the nucleus and the outer electron increases. There's more attraction. Okay, so therefore it becomes harder to remove an electron as you go across. And so as you go across, the first ionization energy increases. Okay, so that's the trends in the periodic table. If we look at it a bit closer, right? So if we were to draw, sketch it out. Right, let's take period 2, right? So if we sketch out period 2 to see trend, and there's a similar trend in period 3, but we'll just sketch period 2. So we're just looking at the first ionization energy here, and we're looking at the atomic number as we're going across the period, okay? So if we take period 2, and we start with 3, and the first elements, we go 3, 4, 5, 6, 7, 8, 9, 10. So this is just across period 2. All right, the general trend across period 2. So the general trend is to increase. So the first element is lithium. All right, and to remove an electron from the next element, beryllium is harder, because beryllium is a smaller atom. Okay, it's got more protons, a greater nuclear attraction. Right, then something unusual happens, and for boron there is a really slight decrease. Okay, but then the trend continues again. So carbon, element 6, carbon is the same increase, and then element 7, nitrogen is increased, but then for element 8, oxygen, there is a slight decrease. Okay, I've drawn that too much actually, because it's only a slight decrease. And then fluorine, it continues, and then neon at the end of the period, it's like that. So the general trend is an increase, the general trend. But you've got these little blips where it doesn't actually increase. Beryllium to boron, nitrogen to oxygen. You've got to be able to say why it doesn't increase at these two places here. So if we look at beryllium and boron, if we take beryllium first, beryllium is 1s2, 2s2, 2s2. So it's 1s2, let's do the 1s. 1s2, 2s2, and then 2p, there aren't any. Right, there aren't any p electrons, just 1s2, 2s2. Whereas if you take boron, the very next element, okay, again, it's 1s, and again, it's 2s, but boron is 2p1. 1s2, 2s2, 2p1, right? So when you're taking the first electron from boron, you're taking an electron from a higher energy level, ever so slightly, because it's increasing in energy away from the nucleus. The 2p orbitals, the 2p subshell, is slightly higher energy than the 2s subshell. So a little bit more energy is needed to remove the 2p than is needed to remove the 2s. Okay, so the 2p subshell, the 2p subshell in boron is higher energy, has a higher energy than the 2s subshell, because remember you fill the 2s first, then the 2s subshell in beryllium. Okay, so it is easier to remove that electron. So it's easier to remove the electron, the first electron from boron. Okay, so you've got this tiny little blip here. So it's only a small decrease, but it does decrease. And again, this is a small, I've not drawn it very well, it's only a small decrease to oxygen. Okay, so why does it happen between nitrogen and oxygen? So again, if we look at nitrogen, nitrogen is 1s2, 2s, this is nitrogen now. Look at nitrogen. Nitrogen is 1s2, 2s2, 2p3. Remember, the electrons occupy the orbitals by themselves, whereas oxygen is 1s2, 2p4, And now 2p4 for oxygen, you have to pair up the electrons. So it's slightly easier to remove that electron from oxygen because there is repulsion between the pair of electrons. So it's easier to remove the first electron from oxygen because of repulsion between the pair of electrons. It's the first one that's been paired. Okay, the paired electron, because there's a repulsion between them, it is easier to remove. So therefore the first ionization energy for oxygen is going to be slightly lower than what it is for nitrogen.